All right, so number 15 has the same directions as number 14. Find the real and complex zeros of our function. So if we take a look at our polynomial, it's an x to the third power, which tells us we will have three, well, total zeros. All right, we look at our graph to see if we have any real zeros. Real zeros are going to be what we see when graphed. Our function is a 0 at x equals -2. So we know that that is a real zero. Which means if we have three total, we have two complex zeros that we have to find. So the way that we find those is we're going to divide our polynomial down. It'll go from an x cubed down to an x squared. And when it's an x squared, we can solve with factoring, quadratic formula. On the last problem, we used square roots. So we have a way to solve those quadratic equations with the x squared. So to divide this down, we're going to do synthetic division. I talked about in the last problem, if you know that x equals -2, then -2 is what goes in the box. The factor would be x plus 2 is a factor of this polynomial, so tricky x, -2 right there. We're going to write our coefficients across the top from our polynomial, so it's a 1x cubed, a -1x squared, a -2x, and a +8. If we had skipped any of those any of those terms, we would have put a 0 in. So just remember, look out to see if you need to add in a 0. So synthetic, you bring your first term down. Going to multiply to the corner. 1 times -2 is -2. Add down, we get a -3. Multiply to the corner for a +6. Add down is negative, not 8. Add down is a 4. Multiply to the corner, -8. Add down 0. Remember, that's your remainder. And I knew that we would get a 0 because if this x plus 2 is a factor, that means that it divides evenly. So any real zeros that you can see on a graph, your function will divide evenly by those factors. So let's fill in our x's from the remainder working to the left. You've got your constant term, your x to the first, and your x squared. So this is that's our new polynomial, new polynomial. We're going to solve that. So x squared minus 3x plus 4 equal to 0, so we can find the complex zeros of our function. So we could, at this point, think about factoring. Are there factors of 4 that add up to -3? Honestly, because we didn't see any other real zeros, I know that I'm going to have two complex, which means we're going to have I, and so that's going to come from square rooting a negative number. So this won't be factorable. We're going to do our quadratic formula with this. So quadratic formula, x equals -b, so we have a -3, plus or minus the square root of b squared, so -3 squared, minus 4 times a times c. Remember, you have a, b, c. This is all over 2 times a, which is a 1. So when we simplify this, this is a +3 plus or minus the square root of. Let's get this down to a single number. When you use your calculator, you have to use those parentheses. -3 squared is a +9. We end up with 9 minus a 16. 9 minus 16 is -7 all over 2. All right, there's that square root of the negative number that I said would happen. So we have 3 plus or minus. We're going to bring in I. Now it's a +7 all over 2. And that's it. We can't do anything with a square root of 7. So we could break it apart. We could say 3 over 2 plus or minus I root 7 over 2. We also could leave it like that. So this is an acceptable answer and this. But if we look back at our problem, those are the other zeros. Let's see, I don't know, maybe I'll do 3/2 plus or minus I root 7 over 2. So 3/2 plus I root 7 over 2 is a zero, a complex zero, and 3/2 minus I root 7 over 2 is the other one. So these are the complex ones. We have one real, two complex, giving us a total of 3. All right, number 16. How do the graphs of the functions g of x equals 3x to the, what is that? 3x to the fourth minus 5 and h of x equals 1/3 x plus 2 to the fourth plus 5 compared to the parent functions. So do you notice how this is an x to the fourth? So the parent function, I'm just going to say, is f of x equal to x to the fourth. No other numbers. That is the parent function. So let's talk about what's happening. If we take our x to the fourth and we multiply it by a 3 out front. So let's talk about how g of x is going to change from the parent function. When we multiply out front, that is going to be a vertical stretch or compression. If this number is greater than 1, we have a vertical stretch. Notice we are subtracting 5 off of the whole thing at the very end. That is a vertical shift, either up or down, because it's minus 5. That means we are going down 5 units. And that's how g of x compares to the parent function. Now, h of x, how does this compare to just an x to the fourth? Well, here's your x to the fourth, but we can see there's a 1/3 out front. The number out front, if you're multiplying out in front, that's a vertical stretch or compression. If this number is between 0 and 1, that is going to be a vertical compression. Okay, then we notice that instead of an x to the fourth, it's an x plus 2 to the fourth. So when we add or subtract numbers in with your x, that is a horizontal shift. Tricky x, if it says x plus 2, that means you will move to the left 2 units. And then this plus 5 on the end is your vertical shift. We are going to go up 5 units. And that's how that compares to your parent function. All right, number 17. Aaron cuts 4 squares with side length x inches from the corners of a 7 inches by 10 inch aluminum rectangle. She folds the remaining aluminum to make a tray that is x inches high. Write and simplify a function for the volume V of the tray in terms of x. So hopefully we are recognizing this problem. We've seen it several times now. So she has a rectangular piece of aluminum right here. This is a 7 by 10. What she's going to do though is she's going to cut out a corner or a square from each corner that is x by x units long. She's going to cut one out here, x by x. These are all x by x's from each corner. All right, to find volume, we need length times width times height. Here's our length, here's our width, and our height happens if we can imagine these fold lines where if we take away this corner, then this piece right here is going to fold up. We'll take away this corner. So there's a fold line, here's a fold line, and here's a fold line. So kind of think about if we have this whole length is 10, but we're going to remove x units here and we're going to remove x units there. So let me see if it will let me. All right, so I'm taking away an x and I'm taking away an x. So what that is it used to be 10 units long, but now it's 10 minus 2 x's. I'm going to go ahead and remove those from the top as well because we would remove those from the top and the bottom. Okay, now this is 7 units long, but we are going to remove an x and remove an x because we're removing that x twice. We are taking out 2 x's. And I'll remove them from the other side. And now we can see this is what it would look like if she cut out those corners, and now she's ready to fold those up to form a tray. So volume is length times width times height. Our length is 10 minus 2x, our width is 7 minus 2x, and our height, they did tell us, is x inches high. But if you can imagine that this gets folded up and this gets folded up, this edge right here and this edge would come together, and this x ends up standing straight up, and we know that our height is now an x. So we're going to multiply these together. Our volume is equal to our length, 10 minus 2x, times our width, 7 minus 2x, times our height of x. So we're going to multiply 3 things together. Honestly, we can multiply them in any order we want. I prefer to multiply the x in first just because it's a quick distributing. So I'm going to go ahead and distribute. We have 7 times x, which is 7x, and a negative 2x times x, which is a negative 2x squared. Put that in parentheses. So all that I did is I just multiplied this and multiplied this. I'm going to carry down our 10 minus 2x, and now we're just going to multiply these two binomials. To do that, we're just going to distribute. We'll do 7x times positive 10, which is positive 70x. 7x times a negative 2x is a negative 14. X times x is x squared. Now let's distribute negative 2x squared times 10 is a negative 20x squared. And then negative 2x squared times a negative 2x is a positive 4x to the third. So we're almost done with this problem. Our final volume, this is our answer right here. I can see we have some like terms to combine, and I'm going to go ahead and put it in standard form. This 4x cubed would go first. Then we can go ahead and combine these x squareds together. Negative 14x squared minus 20x squared is a negative 34x squared. And then that positive 70x plus 70x just goes on the end. And there's the volume of that tray. All right, so we made it to our last problem. We are going to sketch a graph of this function, and then we're going to figure out what's happening on all of these intervals. So let's go ahead and just see what this looks like in our graphing calculators first. We'll get our sketch and then talk about how we fill these in right here. All right, so here's what it looks like on our graphing calculator. Some things that we want to, I wonder if I can make that a little bigger so we, oh, nice. All right, so when we sketch this, we want to first plot where the zeros of your function are. So we can see we have one at a positive 3, a negative 1, and a negative 5. So on our sketch, let's just plot those points. We've got positive 3, negative 1, and what do we say, negative 5? Okay, then what we want to pay attention to is we can see we're coming up from this side. We're going to turn right here. So what is the x value where that's happening? I can see negative 1, 2, 3, just a little bit after that negative 3, we're going to turn. And if I look at our intervals over here, do you see that negative 3.3? that's a turning point of our function. So I am going to go ahead, maybe I'll just draw a vertical line. 1, 2, 3. Here's at about a negative 3.3. That is right here. That's where our function is turning. We can see we have another one right here where our function turns. It turns right there. And if I look at our intervals, I think that that is that positive 1.3. So I'm just going to sketch in one more line at positive 1.3. All right, we can sketch in this function. We are coming from here, hit your, go through your 0. When you get up here, once you get to that, where that turning point is, you're going to turn, come back. I know that this negative 15 right here is your y-intercept, so I can just be aware that we're going to cross the y-axis at negative 15. When you get to that other vertical line, we're going to turn and head back up, and there is a sketch of our function. All right, so when we look at our function right here, maybe I'll get rid of this one. Okay. What I want to point out is where our function is positive and negative. So our graph switches between positive and negative intervals when we cross the x-axis. So here we're negative, we cross the x-axis, now we're positive till we get to our next x-intercept. Now we're negative until we get to our next one, and then we're positive. So we know that these zeros of our function, or the x-intercepts, are happening at 3, -1, and -5. So when we look at our intervals, do you see how right here we're using those 3, -1, -5, and then this one also, here's a 3, -1, -5. That's going to have our graph go between being positive and negative. So when I come over here to fill in these words, I need to use positive and negative. So from negative infinity to 5, so negative infinity is the left side of your graph, all the way up to where x is a 5 right here. So on this side right here, do you see how our graph is below the x-axis, making it negative? And then also from -1 to 3. So between -1 and 3, see how our function is below the x-axis? So our function is negative on those intervals. Now from -5 to +1, so from -5 to -1, we are above the x-axis, so we're positive here. And then from 3 to infinity, which is just the right side of your graph, 3 to infinity, we are positive there. So that's where your function is positive. All right, so the last two, what's happening from negative infinity to a negative 3.3? So from negative infinity to negative 3.3, so these numbers, the negative 3.3, that's that line we drew in. Those are our turning points. So your turning points tell us where our graph changes between increasing and decreasing. So here we're increasing to the negative 3.3, then we're decreasing all the way to the positive 1.3, and then we're increasing again. So when we see these numbers in our intervals that are not the zeros of your function, those are going to be your turning points. So we have to figure out, are we increasing or decreasing on those intervals? So from negative infinity, the left side of your graph, all the way to the 3.3, we were increasing. And then from 1.3, so here's 1.3, to positive infinity, we're increasing again there. So this is going to be, we are increasing on those intervals. And then what's happening between negative 3.3 and 1.3? Negative 3.3 and 1.3, our function is decreasing. All right, there's the end of our ticket to retake review.